Okay, before you watch the video, this was originally supposed to be an entry for 3 blue 1 brown Summer of Math Exposition, but I wasn't able to complete it on time. But you need to know this because this serves as context for the problem I set up at the start of the video, which serves as motivation for everything we do in the video. So, yeah. Let's start off with a scenario. Say you're making a video for some online math video competition, something we all do at some point in our life. Now, you want there to be math content in the video, obviously, but you also want there to be jokes to make the video more engaging. And let's say you have an estimate of the amount of time it takes you to write down and produce a math fact and a joke. And you have 1.5 hours for scripting and 5 hours for production. Let's say for each math fact you get 3 times the number of points than you get for a joke. And you obviously want to maximize your score. It's a competition. What do? Other than give up, which seems really tempting, I won't lie, but it's probably not the best solution. Now, while the above example might not be that relatable, it does introduce us to an interesting subfield of applied mathematics called operations research, which basically helps us make better decisions by applying math to complex systems. And again, the above example might not be that complex, but it introduces us to a type of problems which are very similar in structure called linear programming problems. Here's how. Let's say there are X math facts and Y jokes in the video. We need to maximize our score, which will be equal to the points I get per math fact times the number of math facts plus the points per joke times the number of jokes. Filling in the values, we get our expression. We call this our objective function. So we try to maximize the value of this function under the conditions that the total time of scripting is at most 1.5 hours or 90 minutes. That is, the minutes it takes me to jot down one math fact times the number of math facts in the video plus the minutes it takes me to write down one joke times the number of jokes is less than or equal to 90 minutes. And similarly, the total time of production is at most 5 hours or 300 minutes. So we're essentially optimizing a function under a set of constraints where all the expressions involved are linear. These are linear programming problems, and problems which have this structure come up all the time. Fun fact! Operations research was born from a need to better utilize the resources in World War II. And you know something is useful when we develop it for war. Humans are horrible. Now in the problem we have with us, the number of math facts and jokes will obviously be integers that are greater than or equal to 0. So we can actually find all possible values of x and y that satisfy the constraints. We start by listing all the pairs of x and y starting from 0, 0, then 1, 0 and so on, and we could go on forever, but we don't really need to. See, everything is fine till 15, 0, but x equals to 16 and y equals to 0 does not satisfy the second constraint. So we don't really need to check any pairs with x greater than or equal to 16. Similarly, we list values of 0, 1, 1, 1 and so on, and we generate an exhaustive list of points to check. These are called feasible solutions, by the way, and all we need to do after that is evaluate the objective function at all these points, and the one that gives us the best value is our solution. But it's easy to see how this is not scalable. If we had a problem where the constraints were, say, 10x plus y is less than or equals to 200,000 and x plus 3y is less than or equals to 30,000, the number of feasible solutions will be huge. Moreover, if instead of having an estimate for the time it takes me to write down one joke, I had an estimate of the amount of time it takes me to write a minute of jokes and similarly to jot down a minute of math facts, our variables no longer take discrete values. We now have an infinite number of feasible solutions. And at that point, how do you even start? How do you even find and list all the points? Because honestly, spending an eternity checking all these points one by one sounds like a punishment that the mathematicians who go to hell probably get. Or non-mathematicians. I don't think this is going to be fun for anyone. So we need to look for a better way. Now, graphs often provide keen insight into the behavior of functions, and linear graphs are especially easy to plot. So a graphical solution seems like the next best thing to try. Before we proceed, here's a quick crash course on lines in the xy plane. In the xy plane, lines are represented by the equation ax plus by equals to c, and the particular values of a, b and c decide which line we are talking about. Subtracting ax from both sides and dividing by v, we can rearrange the equation to look like y equals mx plus c prime, given that b is not equal to 0 because division by 0 is not defined, obviously. Here m is the slope of the line, and changing it changes how steep the line is. And c prime is the number at which the line cuts the y-axis. By changing the values of these two variables, we can get any line in the xy plane. Now it is at this point that we make an important observation about linear graphs. Let's say we plot a line 3x plus 2y equals to 6. We draw lines parallel to this original line. These lines will be of the form 3x plus 2y equals to n, because this can be rewritten as y equals negative 2 by 3x plus n by 3, and the slope here is constant. But we notice something interesting. On one side of the original line, all the parallel lines have a value of n less than 6, and the other n greater than 6. So a line not only describes the collection of points that satisfy its equation, but it also divides this two-dimensional space into two halves. A half plane with the point satisfied 3x plus 2y is less than 6, and a second half plane with the point satisfied 3x plus 2y greater than 6. And these expressions are exactly the expressions we have in our constraints. So we now know what linear inequalities look like on a graph. So let's plot our constraints. We'll start with the second one. The total time of production, that is the time it takes me to produce a minute of math content times the minutes of math content plus the time it takes me to produce a minute of jokes times the minutes of jokes, must be at most 5 hours or 300 minutes. Filling in the values, we observe that all the coefficients are multiples of 5. So dividing both sides by 5, we get a simplified inequality. To plot this, we first plot the equation 4x plus y is equals to 60. Now we know one of these half planes represents our constraint, we just need to figure out which one. To do this, we take a random point in one of the half planes, say the origin, and draw a line through it parallel to our original constraint. I know the origin doesn't sound random, but it makes for easier calculations, and that's why I'm using it. You can use any point that is not on the original line. So this line we made will have the equation 4x plus y equals to n, and since it passes through the origin, x equals to 0 and y equals to 0 must satisfy the equation. So 4 times 0 plus 1 times 0, which is equal to n, which is equal to 0, which is less than 60. So the half plane in which the origin lies and this line lies must be the one that corresponds to our constraint. And similarly, we can plot a second inequality. Now we want those points that satisfy both the first and the second constraint. That is, they must lie in the graph of both the constraints. So the region formed by the overlap of both our constraints gives us the feasible solutions. And the number of minutes of something obviously cannot be negative, so we restrict ourselves to the first quadrant. And that's it. We have found the complete set of points that satisfy all of our constraints, using just a very simple observation. I'll be calling this area of feasible points our feasible area.
Excuse me, sir, we have a smaller feasible area now, but that's still an infinite number of points. Smaller infinity than the xy plane, I guess, but still an infinity. You're right. But the thing is, the smaller infinity is much easier to manage than the xy plane. And in fact, the observation that helped us get the feasible area also helped us reduce the number of points to check for an optimal solution to a finite number. Here's how.
Having plotted the feasible area, instead of finding the point which gives us the optimal solution, we just pick a random value for our objective function, say 6, and plot the equation 1.5x plus 0.5y equals to 6. Now at all the points on this line which are inside the feasible area, the objective function will be equal to 6. But more importantly, at all the points in our half plane 1.5x plus 0.5y greater than 6, which are inside the feasible area, the objective function will have a value greater than 6. So we can shift our line upwards, let's say to a point where the function evaluates to some value v. We know that v is definitely greater than 6. But as long as the line has a portion lying inside the feasible area, we can always find feasible points which give a value of the objective function greater than v. So the only way this line does not have some part inside the feasible area and yet gives us a feasible solution is if it passes through a corner. In fact, no matter what the objective function may be, if the optimal solution exists, it will be at a corner point. And because there are a finite number of constraints, there must be a finite number of corner points. And voila, We have successfully reduced the set of points to be checked for an optimal solution to a finite set. And in our graph, the point C gives us our optimal solution. And if we wanted to minimize a function instead of maximizing, all we needed to do was shift the line in the opposite direction. That's it.
But what if we can't plot a graph? What if the number of variables is greater than 3? You ask good questions, my child. If we can't plot graphs, we could algebraically figure out all the corner points and choose the one that gives us the best solution, right? Except not really. I mean, we could, but there's a problem. Say, for example, we had a situation in which there were 15 variables and 15 constraints. To find all the corner points, we would need to solve 155,117,520 sets of equations of 15 variables each, which is a lot of work. Especially when you realize that in real-life problems, there are thousands of variables and constraints. And sure, this is nowhere near the eternal enumeration of hell we sought to escape, but it still seems like a punishment, which is not ideal. So this is where the star of the video comes in.
The Simplex Method.
The Simplex Method is a really clever piece of algorithm that helps us evade the tedious job of checking all the corner points one by one, and instead enables us to reach the optimal solution by exploring only a select few of those points. Here's how.
To do this, we start from a random corner point and move along the edges of the feasible area, jumping from one corner point to a neighboring one such that the value of the objective function always improves. That is, it increases for a maximization problem and decreases for minimization. And if we are ever at a point where the objective function improves along multiple edges, we choose the one with the greatest improvement. Ties are broken arbitrarily. We continue this process till we reach a point where moving to any neighboring point would worsen the value of our objective function. And that's it, we have our optimal solution. And even though this process might not look that impressive in 2 dimensions, where it's easy to visualize which point gives us the optimal solution, it is an absolute lifesaver as the number of variables increases.
Now, before we get into the nitty-gritty details of the Simplex Method, you need to know a few things. 1. How to solve sets of linear equations and how to infer whether you get a unique solution or infinite solutions or no solution at all. And 2, it will help if you work with sets of linear equations in matrix form using row operations, which is essentially just the same thing. It's a different way of writing everything. So it's fine either way, but it helps if you are comfortable with the representation. Now, if you don't know all this right now and would like to skip this part, you can go directly to this timestamp.
Now, if you're still watching, welcome to a simple simplex explanation. A recipe for avoiding painstaking computations. Step 1. We start off by... Okay, this is probably getting a little distracting. Let's ditch the music. And the fancy stuff. Alright. We start off by converting all the right-hand sides of the inequalities to non-negative numbers, which can be done simply by multiplying the inequality by -1 if necessary, which of course also changes the sign of the inequality. And why we're doing this will become clear in a little while. Now, the simplex method also requires that the variables must be non-negative, and although it is possible to deal with unrestricted variables, for the sake of simplicity we'll be leaving that out for now. The next step is to convert all the inequalities to equations, which is done by introducing some new variables. These are called slack variables in less than equal to inequalities, and these are added to the LHS because it is less than or equal to the RHS. And surplus variables in greater than equal to inequalities, and we subtract these from the LHS because LHS is greater than the RHS. Simple. We also introduce artificial variables in greater than equal to inequalities, but I'll get into that in a little while. Note that the conversion of inequalities to equations does not reduce the number of solutions, because the introduction of new variables means that the number of equations will always be less than the total number of variables, and thus we still have an infinite number of solutions. For the sake of standardization of the algorithm, instead of starting at a random point, we start at the origin. And this is where we understand the significance of making all the right-hand sides non-negative. Since we start at the origin, all xi's will be equal to 0, and since all variables are greater than or equal to 0, this step ensures consistency at the start of the algorithm. It is also here that we understand why we add artificial variables and what they really are. You see, in greater than equal to inequalities, the LHS is greater than equal to the RHS. So it makes sense to subtract something from the LHS, but not really to add. But since the algorithm starts at the origin, this would require the surplus variables to be negative. But in the simplex method, all variables must be greater than equal to 0. So for the sake of consistency at the start of the algorithm, we add artificial variables to these equations. But we don't want these variables to have non-zero values at the end of the algorithm. So alongside this, we also modify the objective function to add a very large penalty for each artificial variable, which will be a positive value for a minimization problem and a negative one for a maximization problem. And the algorithm automatically takes care of them. And because these variables are never non-zero in the solution, we call them artificial variables. They're there just for the sake of the algorithm. And the last and most important step, finding the neighboring corner points and traversing the edges to reach the optimal point. Now the corner points in a system of m equations and n variables are obtained by setting n minus m variables equal to 0 and solving the equations for the m variables. These m non-zero variables are called basic variables. Now this video is already long enough, so I won't be going into the proof of this statement, but you can Google it if you'd like. Now to see how the third step is actually done, let's solve our math video time division problem, which needs a better name, but this will do for now. We simplify our constraints by dividing both sides by common factors and then add slack variables to get the equations. At the start of the algorithm, we are at the origin where all xi are equal to 0, thus all slack variables are the basic or the non-zero variables. To organize all this information, it's convenient to use a table, which kind of looks like an extended matrix. We have columns representing the various variables, the rows, the equations, with each cell filled with the corresponding coefficients. A leftmost column for basic variables and the objective function to be optimized written as an equation. Now, at the start of the algorithm, the value of the objective function is 0. And this can be improved by increasing the values of x1 and x2. But the simplex method moves along the edges of the feasible area, which is equivalent to changing the values of the variables one at a time. So we need to select one variable to increase. To reach the optimal solution as quickly as possible, it makes sense to select the variable with the largest rate of improvement. So we do that. In our example, x1 has the most positive coefficient in the objective function, and equivalently, in the simplex table where the objective function is written as an equation, it has the most negative coefficient. So we select the variable with the most negative value in the simplex table. Note, this is for a maximization problem. For minimization, we choose the most positive variable. Now increasing the value of x1 will make it a basic variable or a non-zero variable, but the number of basic variables at a corner point is always equal to the number of equations. So one of the current basic variables must be made 0. To determine which one, we calculate the ratios of the right hand sides of the equations to the corresponding constraint coefficients under x1. And these ratios are actually just the intercepts of the constraint lines with the x1 axis. And x1 must be increased to the smallest non-negative intercept with its axis, because any increase beyond that will make the solution infeasible. And by doing this, we move from one corner point to the next. Now, increasing x1 means that the current basic variable s2 associated with the second constraint becomes 0. We call x1 the entering variable and s2 the leaving variable. The entering variable column is called the pivot column and the leaving variable row is called the pivot row, with their intersection being the pivot element. This is just basic simplex jargon that we need to know, because why not? So the solution at this new corner point is determined by swapping the entering variable x1 and the leaving variable s2. This swapping is done using the following operations. First, replace the leaving variables in the basic column with the entering variable. Second, divide all entries in the pivot row by the pivot element, which is essentially equivalent to making the coefficient of x1 in this equation equal to 1, which is what we do in normal equation solving. And the next step is also what we do in normal equation solving. We eliminate x1 from all other equations. So for all other rows, including the objective equation, we get the new ith row by subtracting from the current ith row the pivot column coefficient times the new pivot row. Now putting in all the values, we can see how this works out for the first row. and similarly for the second row. All these operations are called Gauss-Jordan row operations, which you might be familiar with if you've worked with matrices. We are now at a stage equivalent to the starting of the simplex algorithm with just different coefficients in all the cells. We see that the coefficient of x2 in the objective equation is negative, and thus increasing its value will increase the value of the objective function. So with x2 as the entering variable, we reiterate all the steps we did before. Find the leaving variable using ratios, find the pivot element, apply Gauss-Jordan operations, and all that. Now, after all this, none of the coefficients in the objective equation are negative, and hence there is no variable whose value we can change to improve the objective function. So this last table is optimal, with the optimal solution being x1 equals to approximately 12.27 and x2 equals to approximately 10.91. We have a solution. And in fact, these are the coordinates of the optimal solution obtained by the graphical method. Which makes sense because we should get the same optimal solution irrespective of the method.
And that's it. We can now solve really big linear problems very efficiently. Operations research is really interesting and a very vast field. And there's more to it than just mathematical analysis. You need to be able to make good mathematical models that represent the real world problems faithfully and decide whether a mathematical approach will actually help. For example,
in a study of the check-in counters at a large British airport, a US-Canadian consulting team used queuing theory to investigate and analyze the situation, and part of the solution recommended the use of well-paced signs urging passengers within 20 minutes of departure time to advance to the head of the queue and request priority service. The solution was not successful because the passengers, being mostly British, were, quote, conditioned to very strict queuing behavior, end quote, and hence were reluctant to move ahead of others waiting in the queue. Which I guess perfectly demonstrates how carefully we need to consider situations, not just mathematically, but also psychologically and culturally.
Now from both the graphical and the simplex method, we find that I should make a video with around 12-ish minutes of math content and 11-ish minutes of jokes, which makes a video duration of about 23 minutes. Why don't you check the duration? Pretty close, no? That is the power of maths. Except, not really, it's the power of manipulating coefficients to get the answer you want. I wish I was able to write 20-something minute script in 1.5 hours. Not that efficient. This took weeks. Now I barely scratched the surface of operations research. So if you'd like to learn more, you can read the book Operations Research and Introduction by Hamdi Taha, which is the book I referred to for this video. And thanks for watching. I hope you learned something.